Welcome to the deep dive. Today we're embarking on a really fascinating journey into the world of calixarenes.
Ah, yes, the molecular basket.
Exactly. These molecules, they've become, a real cornerstone of modern supramolecular chemistry.
They really have. Quite a story behind them.
So our guide for this deep dive is the comprehensive text Calixarene by Stoddard. We're planning to explore it chapter by chapter.
Sounds good. It's a great source for tracing their history and development.
Right. We want to uncover the story, from their initial, almost accidental discovery right through to the cutting-edge applications.
And the mission for you, listening, is to get a solid but hopefully engaging understanding.
Yes, without getting totally bogged down in the super complex chemistry if we can help it.
Yeah.
We want you to appreciate their evolution, their potential.
Okay, let's dive in. Where do we start? The name.
Well, the name itself, Calixarene, is interesting. It brings to mind a chalice, right? A vase.
Mm-hmm. And that picture is actually incredibly fitting.
Because they really do have this basket-like structure.
And that shape, as we'll see, is absolutely fundamental. It's key to how they recognize and interact with other molecules.
Definitely. So let's rewind. Chapter 1. From resinous tar to molecular baskets. The story starts way back, doesn't it? Early 1900s.
Phenol formaldehyde chemistry and Bakelite.
Right, Bakelite and Bakelite, 1908. Huge invention. Ushered in the age of plastics, essentially. Got hundreds of patents for it.
But even a few years later, like 1912, there was this review saying, the actual chemistry was still a mystery.
That quote, Über die Chemie des Bakelites tappen wir noch vollständig im Dunkeln.
We're still completely in the dark about the chemistry of Bakelite. It really shows how new the field was.
And those early reactions, they mostly just gave these, messy resins, right?
Yeah, complex stuff. Resols, Novalex, dibenzyl ethers. Very different from the neat little baskets we're talking about now.
So the shift comes later, 1942, Cinca's work.
Alois Cinca, yes. He and Ziegler were looking at how these resins cured hardened.
And they started getting crystalline products, unexpectedly.
That was the turning point. It suggested maybe these reactions could lead to something more ordered than just amorphous tar.
It hinted at more defined molecular structures.
Exactly. That specific conditions could yield discrete crystalline compounds.
Okay, then jump forward to the 50s, Hayes and Hunter.
Ah, their synthesis. That was a really elegant early piece of work. Very controlled.
They used that blocking group, bromine.
Mm-hmm. To direct the reaction, they built this linear chain, 4 phenol units, step by step.
Hydroxymethylation, arylation, meticulous work.
Then they took off the bromine, closed the ring, cyclic tetramer.
But it was a long haul, right? 10 steps.
10 steps, yes. And they got this light brown, solid, high melting point. Their molecular weight estimate was pretty close, too.
What was really key there was the control, the stepwise nature.
Yes, that blocking group showed you could manage the oligomerization, the linking up, and the cyclization forming the ring more predictable.
A crucial step towards making these things on purpose.
Definitely.
But here's where it gets complicated again. Cornforth.
John Cornforth, yeah. Nobel Prize winner later, but this was 1953. He was looking for anti-tuberculosis drugs.
And he repeated Zinc's reaction with Pietert butylphenol.
And surprise, surprise, not one crystalline product, but 2.
2 different melting points.
Right. And he saw the same thing with Pieterdoctylphenol. He called them HOCLOC and HBCLBC, high and low melting compounds.
And the analysis suggested they were both cyclic oligomers. Rings.
So the simple picture starts to break down. What seemed like one reaction was giving a mixture.
Different melting points meant different structures or maybe arrangements.
Cornforth's finding really shifted things. It suggested maybe you weren't just getting the cyclic tetramer, but a mix of ring sizes.
Added a layer of complexity, which of course drove more research.
It certainly did, because initially everyone was excited about that basket shape.
The presumed cyclic tetramer shape looked perfect for molecular recognition.
Binding other molecules selectively, like a lock and key or a glove catching a ball.
And the idea was, we can make a whole family of these baskets just by changing the starting phenol.
Super appealing idea. So naturally, they needed a name.
Eventually, Calixarene stuck, though not right away.
The early buzz was all about this seemingly easy synthesis and the potential for host-guest chemistry.
Okay, fast forward to 1975, Gutsche's initial work.
Right. He reported making what he thought were cyclic tetramers from various phenols.
Based on what everyone thought they knew then.
Pretty much. High-melting stuff that didn't dissolve well. Must be the tetramer. He reported it pretty confidently.
But then, the cracks started appearing. Patrick and Egan's work.
Yeah, they showed these reactions were giving mixtures, not just the tetramer.
Their reinvestigation at Washington University using triptychal phenol, that was critical.
Absolutely. And they started noticing discrepancies, comparing products from the petrolite procedure, an industrial method, with their own.
Differences in melting points, subtle things in the IR spectra that didn't quite match up.
And when they used stabilization, chemically modifying the molecules, and ran chromatography.
Thin layer chromatography, right?
Yes. It confirmed they had multiple distinct compounds, not just different shapes of the same molecule, but different molecules altogether.
Different ring sizes, presumably.
Exactly. The real breakthrough came when they looked closely at that petrolite compound from Peter Gutsche.
They isolated this colorless stuff, very high melting point, simple NMR spectra.
But the molecular weight determination pointed towards an octamer, 8 units.
An octamer. But wait, wasn't there mass spec confusion?
There was a really strong signal in the mass spectrum at Me628 that corresponds to the tetramer.
Okay, so why the octamer conclusion?
Well, it led them to think maybe it's 2 tetramers stuck together weakly, but they kept seeing smaller signals at higher mass values.
Suggesting that 648 wasn't the whole story.
Right, the clincher was derivatizing it, attaching trimethylsilyl groups.
Making it heavier and maybe easier to detect properly.
Exactly. That derivative gave a strong signal at me 1872, unmistakably the octamer.
Wow, so the petrolite compound was an 8-membered ring all along.
Yes. And this discovery just resolved so many inconsistencies that had been around for years.
It meant Zinke probably had the octamer way back then.
And Cornforth's high-melting compound, likely also the octamer. Even Petrolite themselves had been selling an octamer derivative, thinking it was a tetramer.
That's quite something. So the simple picture, the easy route to a family of tetramers.
It kind of evaporated. The reality was these reactions usually give complex mixtures, often with very little tetramer, a bit sobering at the time.
But challenges lead to innovation, right?
Often the way in science. The Washington University group kept at it, tweaking conditions, solvents, bases, temperatures.
And they eventually figured out how to make the tetramer, the hexamer, and the octamer selectively.
Yes, for butyl phenol in good yields. Suddenly, these specific macrocyclic baskets were actually accessible.
So the 1970s, that was really the coming of age.
For the phenol-derived ones, yes. Thanks to people like Kemmerer and Mainz, Ungaro, Andretti, Poccini and Parma, Gutsche in St. Louis.
And meanwhile, you had Ertmann and Hugberg in Stockholm working on the resorcinol-derived ones.
Sorry, the Calixarene octals. So, yeah, that first chapter really sets the scene for everything that followed.
It really does. Shows that scientific process observation, confusion, complexity, then breakthrough.
Mm-hmm. Beautifully illustrated.
Okay, let's move into Chapter 2. Making the baskets. Synthesis of Calixarenes. Now we know what they are. How do we actually build them? It starts with the one-step base-catalyzed synthesis.
Yeah, the sort of classic method, in a way. Just reacting a P-substituted phenol with formaldehyde and a base.
And Peter phenol is the star here, the most studied.
By far. But the conditions matter hugely. The base...
Alkali hydroxides usually work, right? Like sodium or potassium hydroxide.
Generally, yes. And the solvent hydrocarbons, or maybe a product polar ones. And the formaldehyde source, usually paraformaldehyde.
But the big challenge is the product mix. You get tetramer, hexamer, octamer, maybe even the bigger ones.
Exactly. Controlling that distribution is tricky. Temperature, concentration, the specific base, the solvent, it all influences the ratio.
And other phenols, like Peter phenol.
Similar reaction, but often messier products, harder to purify, lower yields generally.
And if you try phenols with, like, electron withdrawing groups, nitro,
carbox, usually doesn't work well. You tend to get intractable amorphous goo.
So non-deactivating p-alkyl groups seem best.
They offer the best chance, yeah. Though even then, it's not guaranteed. Long chains can be bad.
But p-cresol can give hexamer and heptamer.
Reported yields are decent, yes. And p-isopropylphenol apparently gives the octamer, but in very low yield.
It just shows how sensitive these reactions are to subtle changes in the starting material.
Absolutely. Steric effects, electronic effects. It's a delicate balance.
Okay, what about the one-step acid-catalyzed synthesis? How does that compare?
It also gives cyclic oligomers, but it tends to favor larger rings more than the base-catalyzed route.
So different conditions, potentially different dominant products.
Right. Base-catalyzed is still the main way to get the common p-terp-butyl calixarenes, but acid offers another pathway.
Right. Now on to the more controlled methods. Multi-step synthesis. First, the non-convergent stepwise ones.
Like Hayes and Hunter's synthesis we mentioned earlier. Linear, step by step.
That 10-step route to p-methylcalixforene. Painstaking, but flexible in theory.
You could potentially change the phenol unit at each step.
And Kemmer's group in Mainz really ran with this linear approach.
They did. Kemmer came from polymer chemistry, wanted to understand phenol formaldehyde resins by making well-defined bits.
Oligomers, yeah. First linear, then he got interested in the cyclic tetramers.
Did some really elegant work, repeated Hayes and Hunter, and his most crucial finding, perhaps.
The temperature-dependent NMR.
Exactly. Of those bridging CH2 groups. Showed they weren't static, the molecule was flexible. Big insight.
We'll definitely come back to that flexibility. But linear synthesis is slow, which brings us to convergent stepwise synthesis.
The fragment condensation idea. Makes sense, right? Build smaller pieces first, then join them.
More efficient. Boehmer's group at Mainz was a leader here.
Very much so. They developed strategies like the 2+2 synthesis.
Combined 2 dimer units to make a calixforene.
Right. And de Mendoza did a 3+3 for Calixarene.
That's like molecular Legos.
Pretty much. There's even a 1+1+1+1 approach using specific starting materials with Teixel 4.
Titanium tetrachloride. And 2+1+1 methods, too, for making calixforenes with different substituents around the ring.
These convergent routes just make stepwise synthesis much more practical. Better yields, fewer steps overall.
Allows for more complex, functionalized calixarenes. You mentioned Boehmer's irisarenes.
Ah, yes, the baskets with a handle. Exoannularly bridged calixforenes. Shows the versatility you get with these methods.
Okay, the chapter also covers calixarene-related compounds. Things like noricalixarenes.
Where the aryl rings are directly linked, no methylene bridge. Or homocalixarenes, where the bridge has more than one carbon.
So variations on the theme, changing the basic structure.
Exactly. It gives you different shapes, different rigidities, different properties. Norcalixarenes, for instance, can be more rigid.
Then there are homoxycalixarenes and homoascalixarenes, oxygen or nitrogen in the bridge.
Right. That Peter butylda homoxycalixforene pops up in the petrolite procedure mixture.
Is it an intermediate or just a side product?
Still a bit debated, its exact role, but you can make it deliberately by dehydrating a specific linear precursor. Its presence just highlights how complex that one-step reaction really is.
Lots of things happening at once.
Definitely.
And heterocalixarenes, replacing the phenol rings themselves.
Yeah, with things like thiophene rings, calixthiothenes, or pyridine rings, calixpyridines, even silicon in silicalixarenes, or mixtures.
That's where it gets really creative, incorporating different elements.
Absolutely. Putting heteroatoms into the framework lets you fine-tune the electronic properties, the shape, opens up lots of possibilities.
Finally, Chapter 2 touches on the mechanism. How do these things actually form? Base-induced first.
The thinking is, the base pulls a proton off the phenol, makes a phenoxide ion.
Which is a good nucleophile. Attacks formaldehyde.
Right. You start building up hydroxymethylphenols, then linear oligomers linking phenols via methylene bridges, or maybe ether linkages initially.
But the mixture is super complex, lots of non-cyclic stuff.
Dozens of components seen by HPLC analysis. Quinone methide intermediates are thought to be key players in building the chains.
So nucleophilic addition is the start. Phenoxide attacking formaldehyde.
And the base catalysis is generally seen as more selective than acid.
Why is that?
Making the phenoxide activates the ring for attack at a specific position relative to the OH group.
Okay, and the acid-catalyzed mechanism.
That involves protonating the phenol and the formaldehyde. The key step is then electrophilic aromatic substitution.
Where an electron-poor species attacks the electron-rich aromatic ring.
Yes, but it tends to be less selective. You also get similar intermediates, diphenylmethane types, dibenzyl ether types.
Less selective because the acid activates things more generally.
That's the idea. Leads to more potential side reactions, less control over forming just the desired cyclic product.
So Chapter 2 gives us the chemist's toolkit for making these baskets, from the simple, messy one-pot methods to the really controlled multi-step approaches.
And it highlights that trade-off, convenience versus control and specificity.
Definitely need those multi-step routes for anything complex.
For sure.
All right, Chapter 3, proving the baskets, characterization and properties. We've made them, now how do we know what we've got? Starts with melting point.
Seems basic, right? But they give you a first clue. Purity, maybe ring size or conformation influences it. They vary a lot.
Yeah, then pK values. How acidic are they?
Generally more acidic than just a simple phenol molecule.
Why is that?
The OH groups are close together in the calix. This can stabilize the anion, the deprotonated form, Maybe through hydrogen bonding within the molecule?
Makes it easier to lose that proton.
Exactly. Early measurements were tricky, but later work comparing Calixarenes to linear trimers and monomers gave good data.
And the linear trimers are kind of intermediate in acidity.
Often, yes. And putting electron withdrawing groups on, like nitro groups, makes them even more acidic, as you'd expect.
Okay, now the big one. NMR, nuclear magnetic resonance.
Absolutely essential, both proton 1H and carbon 13C NMR.
For symmetrical ones, the 1H spectrum can look deceptively simple.
But then you do temperature studies, like Kimmerer did. Those methylene protons, the CH2, bridges their signal changes from a doublet to a singlet as you heat it up.
Proving the molecule is flexing, right? The rings are flipping or rotating.
Exactly. It shows conformational flexibility and other NMR tricks like NOE experiments.
Nuclear Overhauser effect tells you which protons are close in space.
Right. And looking at how solvents change the signals, Ungara's group did a lot there. Helps figure out the preferred shape, the conformation.
And 13C NMR is good for telling cyclic from linear oligomers.
Yeah, it gives complementary information. NMR is just crucial for structure and dynamics in solution.
What about other techniques, IR?
Infrared spectroscopy. Useful for seeing the OH groups, the aromatic rings, gives characteristic signals.
UVVs.
Ultraviolet visible spectroscopy. Less informative for the basic parent Calixarenes.
Mass spectrometry. We talked about the octamer discovery.
Critical for figuring out the molecular weight, the ring size. Remember the Me648 confusion?
The misleading tetramer signal.
But higher mass signals, and especially derivatizing it, making the ciliated version confirmed the octamer, 1872.
So sometimes you need to modify the molecule to get a clear mass spec result.
Often very helpful. And modern mass spec techniques like MELDI and electrospray are even more powerful now for these big molecules.
For the definitive structure, the gold standard is
X-ray crystallography.
Gives you the 3D picture. Ertmann's early structures of the resorcinarenes, Andretti's first phenol-derived one, Peter butylcalixforene. Huge milestones.
It provides that snapshot in the solid state. Bond lengths, angles, the whole architecture, essential for understanding how they might bind guests.
And finally, the chapter mentions computational methods.
Molecular mechanics, molecular dynamics, using computers to model the structures, their flexibility, how they interact, complements the experimental data nicely.
So chapter 3 is really the analyst's view. All the tools you need to identify these things and understand their basic properties.
It shows you need a combination of techniques for a full picture. Spectroscopy, crystallography, computation.
Okay, leads us nicely into chapter 4, Calixarene conformations, all about that flexibility and shapeshifting. Starts with conformational mobility.
Right. Their ability to adopt different 3D shapes is key. For Calixarenes, those four main ones, cone, partial cone, 1-5-2 alternate, 1-5-3 alternate.
And that comes from rotation around the bonds, linking the phenol rings to the CH2 bridges.
Exactly. Before NMR, people thought the barrier to rotation was high, that you'd have stable conformers you could isolate.
But Kimmerer's NMR work showed.
Interconversion is usually fast at room temperature, too fast to separate them easily.
Depends on the specific Calixarene, though, right? And conditions.
Oh, yes. Ring size matters. Substituents matter. Solvent matters. Larger rings like Calix 6 and Calix 8 are even more flexible.
Calix 6 often likes the cone shape. Calix 8 more of a pleated loop.
That's often observed, yes. Calix 8 is pretty floppy. Thiocalixarenes with sulfur bridges also often adopt that pleated loop.
And the energy barriers for flipping between conformations, they vary.
They do. Thiocalixforene flips more easily than the regular butylcalixforene. Maybe the bigger sulfur atom, weaker H bonding.
And solvent affects the balance between conformers. There's this idea of a broken chain pathway for how they interconvert.
A proposed mechanism, yes. And it's interesting, even just changing the OH groups to methyl ethers on calixforene makes it prefer the partial cone.
Understanding this floppiness is vital because the shape defined the binding pocket.
Absolutely. Flexibility can be good, allows adaptation to guests, but it can also be bad if you want precise recognition.
Which brings us to making them immobile, conformationally immobile calixarenes. How do you lock them down?
The main way is to put really bulky groups on the OHs. Make ethers or esters with big alkyl or acyl groups.
So they physically can't rotate past each other. Steric hindrance.
Exactly. Stops the aryl rings flipping through the center.
And you confirm the locked conformation using
X-ray, definitely. And 1H NMR, again. The patterns of signals for the CH2 bridges and the aromatic protons are often characteristic for cone, partial cone, 1-for-3 alternate.
That chemical shift difference,
Yeah.
day, between the CH2 protons.
Yeah, that's a good indicator, though you have to be careful about solvent effects. 13C NMR of the methylenes helps too.
So by locking the shape, you can design a specific cavity.
Precisely. Tailor-made binding pockets, better selectivity for guests. That's central to supramolecular design.
Okay, but what conformation do you get when you do this derivatization? That's the last part of Chapter 4. Factors governing the conformational outcome, especially O tetrasubstitution of calixarenes.
Right. When you modify all 4 OH groups with bulky groups, which conformer ends up being dominant? It's complicated.
Depends on the group you're adding.
And the reaction conditions temp, solvent, base, even the original P substituent matters?
The base plays a big role.
Can do. Sometimes the metalcation from the base, like sodium from NaOH, can act as a template. It sits in the forming cavity and influences which way the rings orient themselves during the reaction.
So using NaOH and N-propyl bromide on Peter-butyl-calixarene might give you a mixture.
Yeah, reported to give cone, partial cone, and 143 alternate. Controlling it is a fine art.
It really highlights how carefully you have to choose conditions to get the shape you want.
Subtle factors have big consequences for the final structure.
Well, that takes us through the first 4 chapters of Calixarene. A lot of ground covered from those resinous tars.
To understanding synthesis, structure, properties, and this crucial aspect of conformation.
Key moments for me. Definitely the octamer discovery. Realizing the petrolate compound wasn't a tetramer, that must have been a huge shift.
Oh, absolutely. Resolved so much confusion.
And understanding how conformation is controlled. Locking the basket into shape. That seems so fundamental to using them.
It really is. The journey from messy byproduct to these sophisticated, tutable molecules is remarkable.
And their potential. Sensing, separation, catalysis, medicine. We'll get into more of that later, presumably.
Exactly. The ability to tweak their size, shape, functionality, that's their power.
It really is. And thinking about where the field is now and where supramolecular chemistry is going, it makes you wonder, doesn't it?
What are the next unforeseen applications, the next breakthroughs?
Right. Where else might these baskets pop up, blurring the lines between synthetic chemistry and biology even more?
It's a fascinating space to watch. Plenty more to explore.
Definitely something to ponder. Thanks for joining us on this deep dive.